Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Erik Wood of Infineon. We're going to talk today about how to prepare for the coming quantum computing age. Erik, everybody's thought of quantum computing as way in the distance, but the reality is that this is coming on pretty fast, and we really do have to think about how we're going to deal with the post-quantum cryptography, right?
Yes, sir. Absolutely. And the knock-on effects for system design and architecture that are secondary and tertiary effects from implementing new quantum resistant algorithms. Yes.
How soon is this coming? I mean, what's the time frame here? We kept thinking this is off in 2035 time frame.
Yeah, interesting question. So I want to differentiate the specter of quantum computing and how it relates to security as a concept from the actual compliance requirements that are hitting us today, because both are driving the work that we do in the adoption of post quantum cryptography in response to this upcoming quantum computer revolution that's coming. So, from a specter of things, within the next 10 years, it's estimated that there will be on the market commercially available quantum computers that are specifically cryptographically relevant. It's a very new term, but cryptographically relevant quantum computers. That's not going to be your first generation quantum computer. It's not going to be your maybe second generation, but it will happen. There are some first generations now that are demonstrating the science of quantum computing, but there's a lot of problems still. The traditional computing uses ones and zeros. Quantum computers uses a floating memory, essentially, which can be either or. And that's what allows for the efficiencies at an exponential scale of compute. But there's a lot of errors still in that. So when the error correction gets perfected and the processing gets to the speed it needs to be, then all of a sudden you can brute force factor your traditional current state cryptography, rendering it neuter in terms of protecting secrets. And that's the main event for what we're dealing with.
Let's take a closer look.
Sounds great.
Erik, what are we looking at?
In the current state, and mean by today's computing capabilities, there's certain tasks, computational tasks that we can do, and there's many that we can't do, or it would take 1,000 years to do. So they're essentially irrelevant. When we look at to the right side, the illustration, there's a quantum speed up that's happening, exponentially being able to do compute workloads. And those workloads will be beneficial to the advancement of science and medicine and just everyday life stuff, and enabling AI and ML advances. But one of the downsides is that the historic cryptography that we've been using for several decades becomes vulnerable to brute force attacks, as I mentioned. And those workloads to do those brute force attacks, they were all well and good when it would take a millennia to do at the most high-powered computers at the time. But when we look at cryptographically relevant quantum computers, now we can brute force those keys in days. And the challenge there is, okay, let's say it happens in 10 years, but there are, 5-year design cycles for the products that we work with. So an MCU, for example, a microcontroller, is chosen or selected first in a embedded device design. And then it's 2 years for us to make the thing and develop the software, get it out to market. Then it's a year for our customers to design and get out to market, or 2 years. And so really you're talking about a horizon where we need to start thinking about it today. And because of that, there's been quite a bit of industry requirements that have come out now. If you need to sell a chip into a data center market, they want first stage of firmware verification to be supported by a quantum relevant algorithm.
Most people thought this was just for the military and defense industries. Is it moving into more mainstream?
Interesting question. So what I'm seeing, and I interview customers every day on these topics, the data center spurred on by the U.S. NIST and NSA. NIST has defined new algorithms and issued certifications for those that are resistant to quantum computing attacks. And then the NSA has provided a timeline for critical infrastructure, including data centers. So, yes, military, but also data center. And I think the most interesting piece of this is if you look at the Fortune 500 companies, many of them involved in the data centers. I talk to their hardware security people on a regular weekly basis. They are implementing today all their RFIs, RFQs, etc., have requirements for quantum computer resistant firmware verification algorithms. But more interestingly, those companies also make IoT devices. And I'm finding a year lag between the hardware security people at the data center for the same company that makes IoT devices, their counterparts in IoT are about a year behind not behind, but a year lagging in terms of those same requirements getting into IoT, RFIs, etc.
Are these quantum resistant algorithms that are being developed, are they able to fit into these IoT devices? Are they huge? Are they the same size as what we have now, or is it just a completely different formula?
Well, let me dissect that a little bit because you have certain components of that where the answer is yes and the answer is no. So the algorithms themselves fit cleanly into the device. And almost more importantly, the way that we architect our software is in a way that you have an API that faces the customer software, and then they communicate to that API. But we're cryptographically agile to the extent of what's on the other end of that API. So whether we're using traditional algorithms, quantum algorithms, PQC algorithms, etc., there's no difference of what the customer has to do. Now, in terms of memory consumption for the algorithms themselves taking up space on silicon, it's roughly similar. There's a little bit of extra space for some of the algorithms, but then you have to look operationally. So, the earliest PQC, post quantum cryptography algorithms, were good for firmware verification on silicon, but they couldn't do the corresponding key gen or signing operations. You had to do those in an HSM in your PKI system. But the later algorithms like MLDSA and MLKEM, which are the longer term, what we're starting to work to implement options for PQC for firmware verification, signing, and keygen, but then also your secure communications, key encapsulation for TLS, those kind of operations. Then there's a tertiary effect, not just on memory size, where you're talking about the algorithms don't take up much more. However, the signatures that are used based on this are bigger, 50 to 100 times bigger. And what that impacts is certificate sizes that need to be stored on a device. So you need a little bit more memory. In addition to that, there is a hybrid phase that we're going through right now. So it's expected, and the Trusted Computer Group and many others have prescribed now a hybrid time period where you do traditional algorithms and you do the PQC algorithms both. The reason being is because the PQC algorithms haven't been on the market that long. So they haven't been, traditionally 10 years beaten to death to make sure they're okay. But you can do the post quantum for the long term, harvest now, decrypt later defenses. And you can do the current algorithms at the same time. So we're looking at a PQC implementation of a library in ROM, for example, where there's an extra 40 kbytes of algorithm you have to then put in. It's not much bigger than the traditional ones, but you have to do both. Secondly, you have to store bigger certificates. So that's a big deal. And then you have to transfer bigger certificates. In the data center context, you're transferring certificates back and forth between devices as part of the secure protocols for communication in a data center. What's happening is because those signatures are so much bigger, architectures in MCUs and devices in data centers are now moving from I squared C to multiple I3C and eventually landing on the requirement for USB interfaces to support the throughput required to transfer back and forth these much larger certificates now.
So, how big a threat is this really to the average user?
Well, like I said, there's two components of this, and let me show you. So there is the purity of security, and then there's the compliance aspect, right? So from the purity of security, aspect, there's going to be a point in time where cryptographically relevant quantum computers exist, right? And it's going to be one of those kind of 0 day moments. 0 day is a security term, but it's one of those moments where we forevermore will not be able to go back in history and be any way else except for PQC. However, there is the compliance aspect, which is not giving us any sort of flexibility in decision making. If you want to sell to these areas, you have to have this as a required checkbox. On the purity of security perspective, threats are real, right? So, what's happening today, primarily nation states, but potentially others as well, the concept of harvest now, decrypt later. And essentially, what that means is I can take a encrypted packet of data right now and it may provide some information, value, prescribe it how you want. I can store that until a cryptographically relevant quantum computer is available for me to take that same packet of data, which I could not while I was storing it and holding on to it, I could not break into it. But now, in a matter of days, I can. So there's this binary event that's going to happen. And so, from a purity of security perspective, we absolutely need to start doing that today. Now, there's a roadmap for getting this done. Again, we have 10 years. We need to start putting this into embedded products today because of the 4 or 5 year design cycle. And now on the compliance side, we certainly need to make sure that we can sell our products into the markets that we design our products for, whether it's data center or embedded compute, or starting next year, I presume IoT devices will start propagating the requirements for firmware verification. The nice part is when you have a diversified market portfolio of microcontrollers that serve a variety of different areas, we are already invested into IP development and software development to support this for certain areas, and we'll be ready to go when the next areas require it.
You brought up an interesting point, which is that companies as well as countries have been banking this information for quite a while, the stuff that you can't
Yes.
hack today. What sort of impact is that going to cause here? Because you're thinking about this. The last time we had anything even close to this was probably Y2K, but that had a pretty firm
Exactly.
date, and we know what was going on. This is a whole different ballgame.
This is so Y2K was, I would categorize it as in the specter of potential problems. And we had time to get in and do the right thing. And it turned out to be quite a nothing burger. This is similar in many ways, meaning we have time to prepare and we have the attention of the White House, Congress, National Institute of Science and Technology, all the same type of counterparts in our European allies elsewhere. We do have threats. We do have maybe non allies who are trying to steal things for the future. Industrial secrets are a hot topic. Being able to infect data centers is a hot topic. As I said, firmware verification is one of the highest level first order implementations of post quantum cryptography security. And that's because of the data center primarily. So if you think about how the data centers do their security, of course, they have four walls and cameras and security guards and badge entry and all that. But there are moments of time, there are estimated 3 to 5 minutes of time where a bad actor could put in some bad software. And I want to underline that you can put in bad software because these aren't physical attacks, but these are software attacks. And therefore, the security in a data center is all about authenticating firmware before you use it at the time of use. And if you can break that authentication by putting in some bad firmware that can get in and cause problems in the traditional sense, you absolutely need post quantum cryptography to defend against that starting today.
Where do you see these algorithms being leveraged today? What's happening and how is this being put into products?
Let me break that down for you. So what I have here is in the top row, I have the cryptographic relevant operations within a microcontroller. So starting from the left, going to the right, you have three different areas in boot time and then a category of two in runtime. So boot time is from a power on reset where you're bringing up your trims, you're bringing up your device, you're initializing power in the power domains, and your ROM, your read-only memory, is authenticating the first bit of non-volatile memory. And it is authenticating what we call NVM boot. And that's where further trims are applied. And the next step of authenticating your bootloader would happen. Once your bootloader is authenticated, it can look for a firmware update, or if it doesn't see a firmware update available, it can simply continue into authenticating all the runtime firmware or the customer's application. And then in runtime, you're doing all kinds of encrypt, decrypt, attestation operations. And then if you're a connected device, you're doing the security communications, TLS, etc. In today's current state, firmware verification and all the boot time sequence is done using a combination of SHA-256 today for immutable code and ECDSA, which is an elliptic curve based signature verification algorithm and for mutable code. That is moving in the short term to ensure that we have enough resiliency in SHA. 256 is moving to 384. Okay, so that's kind of the first main difference. And then you'll see that in AES, which is your symmetric encrypt decrypt, we're moving from 128 to 256. And those are fairly benign, easy to upgrade topics. But anything based on ECC is going to be going away. And that is hugely relevant in everyday life, from verifying a website that you go to, or in the embedded context when you're verifying firmware or verifying a firmware update or doing any sort of secure communications, TLS, etc. So ECC based stuff is used for all those operations. There's a longer term and a shorter term approach. The shorter term is based on an algorithm for firmware verification. Like I said previously, firmware verification is the very first thing that's being prescribed to protect. And there's an algorithm called LMS or XMSS, which can be used to do that. It's kind of inefficient. It doesn't allow you to do signing or keygen on chip, as I mentioned before, but it's very efficient in terms of just verifying firmware. No secrets are used, so you don't have to have side channel resistance. It's just a verify operation. But longer term, in the bottom row, where we're moving to fully realize the full transition, and I call it CNSA 2030, CNSA being the requirements from the NSA for critical infrastructure and data center that are really the compliance pieces that I was talking about earlier. That's moving wholesale to eliminate the use of ECC or RSA based algorithms in any operation. Like I said, there's going to be a hybrid period, but moving to MLDSA, which is used for signature verification, sign, and keygen on chip. And then you have MLKEM, which is the replacement for the ECC based algorithms that are required for TLS operations. So they do encrypt and sign and key exchange. And so that's kind of the inner plumbing and the transition that's happening over time is moving from the current state to the short-term state to quickly satisfy the CNSA 2.0 2025 requirements, and then ultimately moving to the 2020-30 requirements where everything is available. We'll be releasing massive amounts of products with the 2030 CNSA requirements starting end of 2026. And then this year, we're excited to talk about the PSOC control devices that will be coming out with the LMS support for firmware updates and secure boot. So the verification topic in the short term.
So you're already building this in, but the question is, are you going to be able to keep pace with any changes here that happen in these algorithms? Because you think about AI, for example, and AI
Yeah.
probably will be loaded in here as well with whatever you're doing in quantum decryption and encryption. You've got a lot more tools available now than you ever did before for hacking into these devices.
Yes. So one of the things I mentioned earlier, Ed, if you recall, I talked about crypto agility. And so this is where I have my team architecting everything based around crypto agility because you're to your point, it's going to be changing and it may be changing more than we expect. What if somebody comes along and decides that they figured out a way to practically break MLDSA? Well, then there's going to be some agility required to be able to augment that, right? So the way that we make that user friendly for our customers, right, is that two fundamental things. One is from a software model perspective, we make everything API based, such that they develop their software, it interfaces to our API that then executes down into the black box to run the cryptography. And that doesn't execute down to an algorithm. That executes down to a key ID. And the key ID then drives what algorithm is used. So because we make that circuitous route, we allow the crypto agility to be able to replace keys and replace algorithms. And that becomes transparent to our customers, but more importantly, becomes innocuous in terms of having to change their software. So that fundamentally is one of the biggest things. And then secondly, instead of just providing a library from a third party to our customers to be able to work with to port themselves and to use in software only, we do all the porting ourselves. So we take the cryptographic libraries to support all this stuff. That's the other end of the API. And we integrate that into each of our devices so that the customers don't have to do any work. The libraries are all available in our Modus Toolbox build system, so they can drag and drop, plug and play. And then, most importantly, we do the integration to our cryptographic hardware accelerators. Because as you can imagine, while the code space isn't that much bigger to do a MLDSA versus a ECC based algorithm, the performance is longer. And so it's really imperative to build in acceleration based on hardware to support the speed and performance required to make it kind of a nothing burger for our customers to implement.
So what's happening at the MCU level? This is really where you're coming at it, right?
So essentially, what we'll be announcing is a new product line that we have at Infineon for industrial microcontrollers called PSOC Control. We're now not only delivering all the post quantum stuff we just talked about today in terms of firmware verification and firmware updates and secure boot, but we're doing that in a device that's also platform security architecture level 3 secured.
And just to be clear, this is not just about devices that are connected to the internet. Everybody thinks, oh, we're connected, that's the problem. Devices that are connected to those devices that are connected to the internet as well, right?
Exactly, exactly. Take for example in the data centers, connectivity to the outside world. If you look at the rack and stack in a data center, so there's a single Wi-Fi device that's plugged into the very top of that. It's got an antenna, but there's maybe 1,000 devices in the rack itself. Each one of those devices in the rack itself is talking to one another to do things. Even something as benign as a power supply connected to a server, they care about software security so much in that they have a specific protocol globally for those data center power supplies communicating to the server, and it must do a firmware verify at the time of use before they will allow that power supply to configure itself to support the server. So to your point, it's not just about an outbound IoT cloud interface that's requiring these things.
Eric Wood, thanks for, as always, a great explanation.
Hey Ed, it's been a pleasure. Thanks to you and your audience.